This is video 7.2. It deals with power and efficiency. Once again, our key idea is energy is conserved. It cannot be created or destroyed, only changed from one form into another. So power we have come across in various different contexts before, but it's a really important idea, so it's worth revisiting. It's energy per second. How quickly is energy being transferred? And it's so important we have the idea of rating, a power rating, which is just a posh word for saying this is the power of the device, whatever it is you're concerned with. And just a reminder that the unit is the watt, which is a joule per second. Now over on this side we have efficiency. So efficiency means how good is your device? How good is it at turning your starting form of energy into something useful? Now a lot of effort is put into avoiding dissipation, so losing energy to heat, and two examples here are lubrication, which reduces friction, and insulation, which reduces heat transfer. So here we've got a circuit, and the board specifically mentions this, so that's why we're looking at it. So here we've got our electrons going round. They are delivering energy. We want this to create a motor here, this basic little motor, but we're going to have friction here, and we've got our energy that's dissipating, that's leaking away from our circuit. We're also going to have a heating effect here in the wires as well. So dissipation is losing energy you don't want to lose. So here we have the idea of a power rating. So we've got the panel of this device here, this heater. So it's saying rating, it's 2000 watts. That's its maximum. So when it's working at its maximum, 2000 joules per second are being converted into heat. And we've got an animation of that here. So we've got every second our 2000 joules arrive in electrical form, and they're disappearing into our room, heating it up. So again, here we've got it in clearly stated, hopefully, 2000 joules per second. That's what it means if the power rating is 2000 watts or 2 kilowatts. So here we meet the idea of efficiency. So we can rarely make a device that transfers all the energy into something we want. So our example here is a TV, and we want our TV to create light, and we want it to create sound, but we don't want it to create heat. That's not its purpose, but still a fair chunk of it will inevitably turn into heat. So efficiency then is the useful energy divided by the input energy. So in our example here we've got 100 going in, and our useful is 15 plus 25, the two useful forms, and so that gives us an efficiency of 0.4 or 40%, or put another way, 60% of it is being lost. So here we've got efficiency described in a slightly different way. So here I've got lots of rust on this bearing, and a lot of heat is being lost here. We have to put more energy in to keep it spinning at the same rate. Here we've put some lubrication in, so there'll still be some friction, there'll still be some heat loss, but much less. Now here we've got two containers. They have the same amount of water in, but this one has a very thin wall, and there's lots of energy flying out or being transferred out in lots of directions. Here there is still some transfer, but it's far, far less. So we can see this, or a similar idea, in this diagram here. So here we've got a fire in the middle of a room. This is a top-down view, and we've got this yellow insulating material, and the flow of heat is very slow through this thick section here. It's a bit slower through this one here. Here we've got a thicker section, but a more conducting material. And here's the worst case scenario: very thin, very conducting, and you can see the heat is just flying out. Now we can represent that on a graph. So if we stopped heating this, the temperature would fall, and would fall slowest if the whole building was coated or walled with this kind of material, and it would be quickest if it was the thinnest, fast conducting material. So here we've got a summary, a bit more detail on this. We've got three conductors here that conduct heat very well, and here we've got three insulators. Now insulators do actually conduct, but they conduct poorly, so poorly that we call them insulators. Now the three processes are conduction, convection and radiation. Conduction is particles smashing into each other. Convection is particles actually moving and flowing and rising and falling because of heating causing changes in density, and that's what we can see here. So there's some kind of heat source here, and the free air is allowed to circulate, transferring heat, and water will do a very similar thing. Over here we've got wood, which will conduct a bit. You can see that they're trying to smash into each other, but much more slowly than the metal here, because the metal has free electrons which transfer the heat. Now the trapped air is actually a very good, very effective insulator. It will still conduct a bit, but it can't convect because the air is trapped, and we can't have radiation because it's being blocked as well. So this is a very, very common form of insulation. Finally, we have the vacuum, which is very effective because conduction and convection both have to have particles. They rely on particles, so we can still transfer heat, but it has to be radiation only. So this is really the most effective type of insulation, but it's quite expensive.